I do want to mention I think I'll have to postpone the test to maybe April 7th, that Monday, but I'm not sure. I think most likely I will. So because we'll finish chapter 16 next week, we'll have our review, then you'll take your exam. So I am behind, but it is what it is. It's not your fault. I had a lot of interruptions in my life. Also, we had spring break, and then we had the exam after spring break. So many things are happening. Huh?
The snow days.
The snow days as well, and I may be gone April 8th. I'm not sure. That's a Tuesday, so that's not going to affect you guys.
You human, Dr. A.
Beg your pardon?
That's life. I said you human.
Human. Thank you. I appreciate that. All right, so let's do some titrations together. Did you sign in? Okay. Can you hear me? All right, so if you guys have started your lab on those problems, so work together, work with your group, check the answers with my answers. My answers may have some errors. That's okay. But we just want you to get some practice on titrations. So you guys have done a lot of titrations in the last lab. You've done like 4 or 5. Definitely, if you had Chem 1 here, you've done titrations. Let's do some titration problems. All right, so exactly 100 mLs of HNO2. Thank you, Marche. All right. So what I'll do is probably give you 5 extra points on your homework, okay, which builds up. So 100 mLs of 0.1 molar HNO2, which is a weak acid, is titrated with 0.1 molar NaOH. So titrated with means that the NaOH is in the burette. You know what a burette is, right? It's that long tube that you do the drops. Okay. So the 0.1 molar NaOH is here. We're going to add it. This is a strong base. Okay. This is a weak acid. So we're going to add strong base to a weak acid. The weak acid is 100 mLs of 0.1 molar HNO2. The strong base, we're going to add whatever we add. Okay. So first problem is, what is the initial pH? No NaOH is added. So there's 4 phases here. Okay, 4 phases. The first phase, nothing of the titrant is added. Nothing. Okay, this is literally at 0.00. Nothing has been added. So what we have here is the pH of HNO2, and we'll do the pH calculation of that. All right. So we've done a lot of these in the last chapter. Okay, it's the same thing. We have 0.1 molar we have 0.1 molar HNO2. So this is going to be 0.10 molar. Okay, no titrant is added. Okay, nothing is added. This is phase 1. Okay, we don't worry about water. It's a liquid. This is 0 and 0 minus x plus x plus x. So this is 0.10 minus x plus x plus x. Okay. So do you guys know how to do this now? All right. So we're going to plug this into our Ka. Okay, I'm going to move this up here. Ka is equal to H plus, which is just like HNO3, same thing. Which H plus, which is just like H3O plus. The way I'm teaching it is like these are one and the same. NO2 minus divided by HNO2. All right, the Ka, I'll give you the Ka. It's 4.5 times 10 to the minus 4. Okay, H plus is, H3O plus is X. NO2 is x. X times x is x squared divided by 0.10 minus x. All right, so on the test and on the quiz, homeworks, you can use the low ionization assumption. Okay, So we will assume x is small. When we assume x is small, 0.10 minus x is 0.10. So we don't do the quadratic. You can do this on my exams. 4.5 times 10 to the minus 4 equals x squared divided by 0.10. X is 4.5 times 10 to the minus 4. Okay. All right, so I'll go ahead, just in the interest of saving some time, I'll go ahead and tell you what that x is. So when I do this on my calculator, I'm getting x equal to 0.00671 m when I square root 4.5 times 10 to the minus 4 times 0.1. That is what that equals to on my calculator. Okay, but what is that x? What does this x really mean? Okay, this x is, it's NO minus, NO2 minus, but what else is it also? Okay, so pH is minus the log of the concentration of H3O plus. Okay, minus the log of 0.0067. 0.00671. And you can check my calculations, but this is what I got. I got 2.17. All right, just to save some calculator time. All right, so you can check your answers with your homeworks, check your answers on the lab, but this is, here I'm interested in how you solve the problem, okay? And on the test, okay, if I see this and you get the wrong answer, I'll still give you correct partial points, okay? All right, so that is nothing has been added, okay? Make sure you use the low ionization assumption. We've done this before. Part B is something that's different, okay? Part B is now we will add 80 mLs of the NaOH to the HNO2, all right? So this is something I need everyone's attention here on, okay, how we do this problem. So we add 80 mLs of NaOH to this. Okay, so the first thing I want you guys to do is calculate the concentration after mixing. This is part B. Okay, so what is the concentration after mixing? Alright, so we'll have the concentration of OH minus. Okay, so everyone just be with me for these few moments here. Okay, we have 80 milliliters of 0.1 molar NaOH. Okay, 80 milliliters times 0.1 molar NaOH. Okay, the sodium ion is spectator. Okay, what is our total volume? 80 mLs plus 100 mLs. So what is our total volume? 180 mLs. Okay, so after you mix 80 mLs, after you mix 80 mLs with 100 mils of this, you have 180 mLs. All right, so mils cancel, you're left with molar. So what's 80 times 0.1 divided by 180? Okay, just to save some time, I got 0.0444 molar. All right, same thing now. We have the HNO2 sitting here. Okay, in part B, we added 80 mils to this. 80 mils to this. Okay. All right, so everyone be with me for a moment. 100 mLs times 0.10 molar. Okay, what is our total volume? 180, correct? Okay, so 100 times 0.1 divided by 180. On my calculator, I'm getting 0.0556. Okay, again, don't worry about the calculator. Worry about how we solve this problem. Okay. right, so we added NOH minus to this. Okay, what is our reaction? This is the second important point I want you guys to be, focus with me on. All right, so we have HNO2. We added 80 milliliters of OH minus. So I'm just going to write it as OH minus. Okay, because Na plus is not really involved in this. All right, so I have a question for you guys. What is OH minus? Is it a strong base? So what will it do? It's going to take this proton from the weak acid, nitrous acid. Nitrous acid is HNO2. Okay, when it grabs that proton, it will give you H2O liquid plus NO2 minus. Okay, so this is the reaction that happens with this weak acid and that strong base. Okay, the Na plus is spectator ion. What's the concentration of HNO2? 0.0556. Okay, what's the concentration of OH minus? 0.0444. Okay, don't worry about water, it's a liquid. All right, now I have a question to ask you guys. I'll pick on you, Sam. Okay, we know OH minus is a strong base, correct? So how much of this weak acid HNO2 will it eat up, will it take? How much? It's strong.
All of it.
All of it is correct. Okay, all of it is 100% correct, but how much is all of it? Yes?
0.05556.
But you only have 0.0444. So all of it in this case is 0.0444. Okay, the units are big M. So this is before the equivalence point. The strong base eats all of it, as you correctly stated. Our classmate correctly stated. All of it in this case is 0.0444. All right, so 0.0556 minus 0.0444. I'll just do the calculator for you guys here. 0.0112 big M. Okay, the units here are big M, moles over liter, and this is 0.0444 big M. Okay. All right, now, next question for you guys is, I have HNO2 present and I have NO2 minus present. I have the weak acid and I have its conjugate present. How will I calculate the pH? Okay, what equation do we use? Okay, we have this and this in the titration. We have some of the HNO2 at 0.0112. We have some of the NO2 minus at 0.0444. So what equation helps us calculate the pH when we have in our presence the weak acid and its conjugate? All right, this is called the Henderson-Hasselbalch equation. Okay, so this is the Henderson-Hasselbalch equation. I'll give it to you on the test, and the Henderson-Hasselbalch is pH is equal to pKa log, drop the acid, which in this case is HNO2. That's NO2 minus. Okay. So this is the equation you'll use. What else do we have here? If we have a buffer, if we have a weak acid and its conjugate, we have a buffer. Okay, we have a buffer. Okay. So buffer here. Okay, for buffers, this is the ideal equation to calculate the pH. So pH is minus the log of Ka, which is, I'll give you the Ka, 4.5 times 10 to the minus 4. Plus log, okay, what is the HNO2 concentration? 0.0112. What is the NO2 minus concentration? 0.0444. Okay. So doing minus the log of 4.5 times 10 to the minus 4 in our calculator, I'm getting 3.35. So again, just to save some time, I'll just do the calculations here. 0.0444 divided by 0.0112 on my calculator, I get an answer. I take the log of that, I get 0.598. So just check your answers if you have, my answers if you have the time, but I'm getting about 3.95. 3.95 if you round it, I guess. So the key here is to use the Henderson-Hasselbalch equation. All right. And like Samantha says, the strong base will eat all of it. All of it. All right. So this is the scenario where it's before the equivalence point. All right. So now we will go at the equivalence point. Okay. So I need everyone's attention for this as well. At the equivalence point. What does this mean, at the equivalence point? Okay, it means the titrant concentration is equal to the titrand concentration.
Is it always indicated by a color change? Do you add something?
Yeah, at the equivalence point you will add something to get a color change, correct. That's when you know all of this has reacted with all of that. That is correct, very much so. And they add a dye or a color, yeah, correct, indicator. So at the equivalence point, the titrant in this particular problem, it's OH minus equals the titrand, which is HNO2. Right, so OH minus, heavy M1, you remember this equation, M1V1 equals M2V2? So at the equivalence point, M1V1 for OH minus equals M2V2 for HNO2. So the M1 for OH minus, you guys remember, is 0.10 molar. Okay, we need to know how much volume of this to add to neutralize it. You're correct, Samantha or Sam. M2 is 0.1 molar. Volume is 100 mLs. So 0.1 times V is equal to 0.1 times 100. So if you solve for V, you'll get 100 mLs. Okay. All right. So it takes 100 mLs. Let me just write this down here. It takes 100 mLs of 0.1 molar OH minus to completely react with 100 mLs of 0.1 molar HNO2. This is at the equivalence point. All right, so what is the concentration after mixing? All right, we'll first do OH minus. All right, so we have 100 mLs of 0.1 molar NaOH. Okay, what's our total volume here? Total volume divided by the total volume. So 100 mLs of NaOH or OH minus plus how much HNO2? So 100 plus 100 is 200 mLs. So this is going to be 0.05. I'll put 0.050 molar. All right, what is the concentration of HNO2? It's the equivalence point. So what's the concentration?
Same.
Same, okay? So the pH at the equivalence point is 0.050 molar. All right, so what is the reaction that occurs here? Okay, the reaction is, let me just go here. Okay, the reaction that occurs is HNO2. Okay, this is part C at the equivalence point. Plus H2O liquid. Oh, I'm sorry. This is not the reaction. Okay. HNO2 aqueous plus OH minus. Goes to H2O liquid plus NO2 minus. Okay, so this is the reaction that happens when you add 100 mLs of NaOH. It's the same as part B when we added 80 mLs. So, all right, so what's the concentration of HNO2 in this problem? 0.05. Okay, what's the concentration of OH minus? 0.05. Okay, don't worry about the water, and this is 0. All right, I'll ask you this question, Samantha, or Sam, sorry. How much of this strong base will eat up this weak acid?
0.050.
All of it, which is 0.050, correct. Okay, but we have a problem here. Okay, what is our problem? Okay, we have a major problem here. Okay, what is that problem? We have a 0. Okay, we have a 0 here. So how will we solve this problem? How will we get the pH? Okay, let me give you a hint, okay? This is an equilibrium, so it can go this way, but what else can it go? Okay, the other way. So at the equivalence point, what reaction will you use, Susanna? What reaction will you use? Okay, this is an equilibrium going this way. It's 0, but we can't have zeros. You're going to use the back reaction. Okay, so that's the key. So at the equivalence point, you will use the back reaction. Okay, so let's use the back reaction, which is H2O liquid plus NO2 minus aqueous gives you HNO2 aqueous plus OH minus aqueous. All right, and this is at 0.050 molar. Okay, don't worry about water, it's a liquid. Okay, and this is 0 and this is 0. Now here's another question. Okay, this will give you a lot of extra credit if you, or it will be really impressive if you know this. Okay, what type of reaction is this? Here we have this conjugate weak base reacting with water, giving you OH minus plus HNO2, the conjugate acid. What type of reaction is this?
Redox reaction.
Huh? So this is H2O is being the acid. This is the weak base. Okay, you give HNO2. Okay, so this would be the conjugate base. This is the conjugate acid. Okay, this is the conjugate acid to this conjugate base. But what type of reaction is this? What type of K is this? Is it Ka? No, it's not Ka. It's not Kw. Okay, what will it be? Excellent, it's Kb. But how will we get Kb when they only gave us Ka in this problem? Okay, how will you get Kb? What's that relationship? This is Kb, you're right, Sam, but how will we calculate it when they only gave us the Ka of this? Do you know that relationship? Ka times Kb is equal to? Very good. Okay, good job. Ka times Kb is equal to Kw. So not only at the equivalence point you'll use the back reaction, but this back reaction is the Kb. Okay, very nice job. All right, thank you. All right. So Kw is 1.00 times 10 to the minus 14. Ka is, I'll give you the Ka, it's 4.5 times 10 to the minus 4. So I'm getting about 2.22 times 10 to the minus 11, okay, for the Kb. All right. So you're correct, Susanna. You have to do the back reaction at the equivalence point. You're correct, Sam. This is Kb, but how will you find Kb? Okay, you solved that for us, Marche, so I appreciate that. Ka times Kb is equal to Kw. Okay, so this is the Kb reaction. All right, so we don't worry about water. This will be minus x plus x plus x. All right, so at equilibrium, this will be 0.050 minus x plus x plus x. All right, we'll plug that into our Kb. So Kb is 2.22 times 10 to the minus 11. Okay, OH minus is x, HNO2 is x, x times x is x squared, divided by 0.50 minus x. Okay, we're going to use the low ionization assumption here. Okay, so 0.050 minus x is about 0.050. So 2.22 times 10 to the minus 11 is equal to x squared divided by 0.050. Okay, we will square root that. And what is that on our calculator? I'm getting 1.05 times 10 to the minus 6, big M. Okay, 1.05 times 10 to the minus 6, big M. Okay, but what is that x? What really, truly is that x? Okay, it's HNO2, but what else is it also, Susanna? OH minus. So let's calculate the POH. Okay, let's calculate the POH. Because we know POH is minus the log of OH minus. so minus the log of 1.05 times 10 to the minus 6. Okay, what do you guys get when you do that on your calculator? I'll do that really quickly. Getting 5.97. Okay, this is not the answer. Okay, what is the answer? That's POH. So what's the pH?
14
Very good. Okay, so yes, Neil. pH is 14 minus this. I'm getting 8.02. So this is what we do at the equivalence point. Okay? All right, so multiple things going on here. Okay, number one, you have to calculate the volume where they equal. That's M1, V1, M2, V2. Calculate the concentration after mixing. Realize it's 0. So what do you do? As you mentioned, use the back reaction. And then you realized that it's KB now, and then A times KB is KW. Do the same thing we've done before. Calculate POH. And then from POH we get pH. Okay, all of this happens at the equivalence point. All of this happens at the concentration where the titrant is equal to the titrand. All right, our last phase of the titration is after the equivalence point. Okay, so that's on page 8 of our notes. All right, after the equivalence point, okay, 105 mLs of NaOH. All right, so let's quickly do this one. All right, first thing is we'll calculate the concentration after mixing. We'll first do OH minus. 105 mLs. Okay, what's the concentration of OH minus? Okay, 0.10 molar at the very beginning of the problem. Okay, what's our total volume this time? Okay. 105 plus how much? 100. So what's the total volume? 205 ml. Mils cancel, and I'm getting 0.0512 big M. We'll do the same thing here. This is 100 ml of 0.1 molar. What's our total volume? What's our total volume? What's our total volume? Say that again. 205. Okay, 205. Okay, we add 105 mLs to 100 mLs of HNO2. So 100 times 0.1 divided by 205 is 0.0487 big M. 0.0487 big M. Okay, so the mils cancel, mils cancel. Okay, leaving us with capital M, big M, moles over liter. Okay, what is our equation? Okay, our equation is HNO2 plus OH minus goes to H2O liquid plus NO2 minus. Okay, so in the previous problem we had to do the back reaction, which as you mentioned, Sam, was KB. Here we add 105 NaOH, OH minus to the HNO2. This is our reaction. Are we going to use the back reaction here? What's the concentration of OH minus? 0.0512. What's the concentration of HNO2? Okay, don't worry about the water. All right, I'll ask you this question. I'll ask you this, Sam. How much of this strong base will eat up this weak acid? If you say all of it, that's correct, but how much is all of it?
0.04 is the lower number.
It is going to be 0.0487. Very good. Right, so this is 0. What's 0.0512 minus 0.0487? I'm on my, I think it's 0.00242 big M. Okay. And this is 0.0487 molar, moles over liter, big M. Okay, so how will we calculate the pH here? I say, before calculating the pH, let's calculate what? Let's calculate the pOH. Okay, let's calculate the pOH, which, as you guys know, it's minus the log of OH minus the log of 0.00242, and I'm getting about 2.62. Okay, this isn't the answer. Okay, what is our answer? Okay, because this is the pOH. To get the pH, we minus 14. And that's about 11.38. Okay? And that is our answer. All right. So nothing added was part A. Part B, before the equivalence point, we did Henderson-Hasselbalch. At the equivalence point, we calculated the volume. We used the back reaction. We found out it was Kb, and then we used Kw equals Ka times Kb. This is at the equivalence point. Okay, after the equivalence point, what do? Okay, we have excess OH minus. We have excess titrant. We can go ahead and calculate pOH, and from pOH we'll calculate pH. Okay, so this is how you do a titration problem, all 4 windows, okay, all 4 phases. All right, so we have a practice problem, calculate the pH at the equivalence point. I'll let you guys do that on your own. I'll post the answer up on Canvas. But remember, at the equivalence point, it's not before, it's not after, or it's not when nothing is added. It's at the equivalence point. So you want to do the back reaction. Remember, the titrant is equal to the titrant, its concentration. And methylamine with HCl. So I'll give you the answer later. Just I'll let you guys have this as practice. Okay, for HCl, it's a strong acid, so it's going to be H3O plus. Okay, and then this is the reaction. So from there, you can calculate the ice table, use the back reaction, and then, yeah. All right, so I will post this on Canvas. You guys use this as practice. Okay, this is what happens at the equivalence point. All right, practice at home. I'll post the answer. Check your answer with mine. Let's see the last 10 minutes or so. Let us do the final bit here, and that is KSP. Okay, KSP. All right. All right, so KSP is a solubility product constant. Okay, so how many K's have we talked about here?
87.
Sorry?
At 87.
87? Close, maybe 4 or 5. So we first did K, C, that stands for concentration, K, P, gases, pressures, okay, if you have a gas, KW, there's KA, KB, and now I want to teach you KSP. So on your I don't know if I told you this, but there's a KF for complex ion formation. You can skip that on your lab problem set. Okay, I'm not going to test you on that, and you can skip it. Okay, but there's also a KF, complex ion formation. I'm not going to talk about that. All right, so let me teach you KSP here. So for KSP, you're going to link it with a sparingly soluble solid. It's a solid that goes back. Okay, remember in that lab you took the white calcium iodate, you put one part in 40 mils water, put the other part in 80 mils water, the other part you just saved in case something went wrong. Okay, so calcium iodate, just like all these other guys, are solids, but the solids can go back to their ions. Okay, so let's take an example. Okay, so what you guys should see here for KSP, okay, you should see a solid in the reactant side. You guys should see a solid in the left-hand side. Plus, as we know, we all have an equilibrium here. Okay, so the solid is going back to its ions. Okay, that is KSP. I'll give you the KSP, and if you look on page 12 of your notes, there's a whole bunch of KSP constants. I'll give you the KSP. Okay, let's go over a hard one here, the calcium phosphate. Okay, once we do the hard one, I think the other one should be easy. Okay, so calcium phosphate is a solid. Okay, that's in an equilibrium with its ions. So it's what we're going to call a sparingly soluble solid, a solid that goes back. So some of it can go back to calcium ions, which is calcium plus 2. Okay, remember that from Chem 1. Okay, plus phosphate ions, which is PO4 minus 3. Okay, remember that from Chem 1. These two combine to give you calcium phosphate. But some of that calcium phosphate goes back to give you free calcium ion and free phosphate ion. Okay, we always balance. Okay, doing this as an example here. Okay, we always balance. So the calcium is 3 here, so we'll put a 3. The PO4 as 1 unit is 2, so we'll put a 2 here. Okay, 3 times 2 is 6. 2 times minus 3 is minus 6. 6 minus 6 is 0. 0 here. Okay, so some of this calcium phosphate solid, sparingly soluble solid, will go this way. Okay, we're going to say plus S. S stands for solubility. Not X, but S. Okay, but it's not S. How much S? Very good. 3S. And this is plus S, but how many S? Nicely done. Plus 2S. Okay? So instead of X, they use KSPS for solubility. How much of that solid goes back, dissolves back into water as its component ions? We'll plug that into the KSP, okay, which is calcium ion. Okay, don't forget to cube it. Like I said, this one is a little bit harder because it's a 3-to-2 ratio. And PO4 minus 3. Okay, don't forget to square it. Products over reactants. Okay, do we put any reactants here? No, because it's a solid. Alright, so we're going to put 3S in here and 2S in here. I'll give you the KSP. Okay, I'll give you that on the exam for calcium phosphate or any sparingly soluble solid. It's 1.2 times 10 to the minus 26. This is going to equal to 3s cubed, 2s squared. Okay. So we will solve for s here. Okay, 1.2 times 10 to the minus 26. Okay, I'll give you that number. Okay, 3s cubed is 27s cubed. 2s squared is 4s squared. Okay, 27 times 4 is 108. S cubed times s squared is s to the 5th. Okay, so now we will solve for s. Okay, you don't take the square root. Okay, you will take the 5th root. You don't take the first root, you don't take the square root, you don't take the cube root, you don't take the 4th root, you take the 5th root. Okay, so 1.2 times 10 to the minus 26 divided by 108. Okay, you're going to raise it to the power of 1/5, also known as the 5th root. .2 times 10 to the minus 26 divided by divided by 108. Okay, you're going to raise it to the power of 1/5. And you get 2.57 times 10 to the minus 6, right? 1, 2, 3. Okay, here the solubility is in molar. All right, so the solubility, how much of this is dissolved in water? Solubility of calcium ion in calcium phosphate is going to be 3 times this S. .70, something like that, times 10 to the minus 6 big M. And then the solubility of PO4 minus 3 is going to be 2 times this. And what is that? That is 5.14. 5.14 molar. So let's say we have 1 liter. Okay, 1 liter of calcium phosphate, and it's a big white solid. Okay, out of that 1 liter of calcium phosphate, you have a beaker of calcium phosphate, and it's a solid. Okay, and you take that solid calcium phosphate and you put it in 1 liter of water. Okay. In that 1 liter of water, some of it will go back to give you 7.7 times 10 to the minus 6 molar. This is dissolved in water. Some of this solid will go back and give you 5.14 times 10 to the minus 6. This is what gets dissolved in water. This is how much goes back. So the calcium phosphate is not just calcium phosphate as a solid. If you put some water in, some of that water will give you calcium ion in 1 liter. Some of that water will give you phosphate ion in that 1 liter. Okay, so we're solving for the solubility. How much of that S solubility, how much of that solid goes back into the dissolved ions? All right. So this is a little bit more complicated one. The other ones, like AgCl, is a lot easier because it's just a 1-to-1 thing. Okay. If you look at AgCl, it gives you 1 ion Ag plus and 1 ion on Cl minus. All right. So yes, it's 10:50. So have a good weekend and work on your chapter 16. And yes, take care. Okay. So I will probably move the exam again. Just check your Canvas announcements today or Saturday.